Okay, so in the previous lecture we talked about two connected graphs, and one of the consequences of the theorems that we had was the following theorem of Whitney, saying that graph is two connected if and only if for any distinct vertices VW of the graph G you have at least two internally disjoint paths connecting V and W. So you can always find two paths from V to W whose internal vertices are all, no internal vertex of vertex of the other. In Menger's theorem, in this section, we're gonna prove a generalization of that theorem for higher connectivity. So for that, we will talk about disjoint paths, right? So you have a set A and B in a large graph. I want to find many paths, but none of them are pairwise disjoint, and none of them shares a vertex. All right. Now the question is, when do we have? So if we have let's say you have 4 cities here, another 4 cities here. Okay, you can say these are where the soldiers are, these are where the war is happening, so you want to send them as efficiently as possible. And when you want to find this in the train networks, right? So you might have a huge graph, right? The large train networks, and when you want to find is like path, but let's assume for simplicity that two people cannot share the same, cannot use same vertex or same edge, but in this case same vertex, let's say. So you really don't want to have any traffic jams in order to send people as efficiently as possible. How can we do that? So that's kind of topic that we're gonna discuss today. And there's something called max flow mean cut theorem, which is also which can be also seen as a generalization of Menger's theorem. So the one question is, how many vertex disjoint paths can we have? So in other words, what is the maximum number of vertex disjoint paths? From A to B. Okay. Now, one way to prevent having too many vertex disjoint paths is to actually find the cut, right? Find the set of vertices. If I find the set S of vertices separating A from B. So what I mean is, if I delete S, I no longer have any paths from A to B. So we say a set S is separating A from B if G delete S has no paths from A to B. Okay. Now, if we do have a separating set, and then any path from A to B must use at least one vertex. Some paths may use S twice or 3 times, right? But any path will have to use S at least once. So that means if S separates A from B, then the maximum number of vertex disjoint paths from A to B I mean, if you have any collection of vertex disjoint paths from A to B, it has to have size at most S, right? I mean, you cannot have more than S size of S many disjoint paths. Why is that? Because every single path must intersect S. Of course, there are situations where A and B intersect, right? So if this is A, this is B, and we have to allow a path of length 0. Right? So initial vertex and last vertex could. So we are not assuming that A intersection B is empty. I mean, they may have intersections, but all right. Now, so that means we deduce the following, right? So maximum number of vertex disjoint paths from A to B is always less than or equal to minimum size of set S, where S separates A from B, right? And S is the vertex set. Okay. Now, what's surprising is that the equality actually holds. So that's the theorem of Menger in 1927. Okay, so let G be a graph, and A, B be the vertex set, and I don't care whether they have intersection or not. Then let me say this way: so the maximum number of vertex disjoint paths from A to B is equal to minimum size of S, where S is the vertex set and S separates A from B. Okay, and actually, so this kind of theorem has been studied in also in 1950s or 40, late I think it's around 50s, and I'm not gonna say exact formulation. So this is something called the Max-Plominka theorem, where the United States of America were studying the Russians, Soviet Union people were studying how to send troops to the border as efficiently as possible by finding many paths, whereas the US was studying the dual problem, how to reduce the capacity by destroying some locations, like where to bomb in order to prevent moving of the troops to the border in the Soviet Union. And it turns out that their optimum value was same, even though they studied different problem. One problem was to send as many people as possible by finding many paths, and the other was to destroy as small as possible so that nobody can move from this source to target. Okay, so this was discovered by, I think I saw it on the website of Lex Schreiber, and he actually found the documents, unclassified documents, both in Soviet Union and the United States, showing how they study these railroad networks. And they study the railroad networks of the Soviet Union, and both had a different objective, but the outcome will be same because of the theorem. All right, so that's the Menger's theorem. I will prove in a slightly different formulation, which will be more convenient for us to prove. So how do we prove that maximum of something is equal to minimum of something? Right? So this direction is already trivial. So it's enough to prove that, right? So how do we prove such a thing? Well, what I'm gonna prove is the following statement. Okay. If G has no set S of size at most K separating A from B, okay. Oh, okay, let's remove the equality. So what does that mean? This means if the right hand side is at least K, that's what I mean. If the right hand side is at least K, then if the theorem is true, then the left hand side should be at least K. Then G has at least K vertex disjoint paths from A to B. So that's what we claim, right? So I'm saying that if graph has the right hand side of this equation is at least K, then the left hand side should be at least K. And I can use K for any value, any integer. So if that's the case, then we prove this inequality. Okay? So that's enough. All right. Now, why do I use this formulation? Because it will make induction easier, because I can fix K and I apply induction on, let's say, number of edges, maybe, or something. Okay, I can always choose induction parameter later, so I can, let's say, induction on something, blank. Let's fit it later. All right. So first of all, let's simplify the situation by saying if A intersection B is non-empty, then let's do something, right? If A intersection B is non-empty, okay, so if we have some elements here, what do we do? Then let G prime, let's delete the common elements, A intersection B, and then K prime be a K minus size of A intersection B. So we delete this part from the graph G, and now by the induction, by the hypothesis, I don't have any set separating A minus this thing. So let's say A prime is A minus B and B prime is B minus A, and I don't have any set S of here separating A prime from B prime if it has size less than K prime. There's no such thing, because otherwise this together with the intersection will have no path from A to B. So that means G prime has no set S prime separating A prime from B prime of size less than K prime. So that means G prime has at least K prime many vertex disjoint paths. From A prime to B. And now for the people in the intersection, you have a path of length 0, so there's nothing to worry. So I can add them into the list. So G has at least K vertex disjoint paths. From A to B. So we are done. Okay, so that's one case where we know we prove it. But why does it work? We apply induction hypothesis and we are deleting intersections. So we have to, when you choose induction parameter, we need to choose the one that must decrease by doing this thing. And when you delete intersections, there is no guarantee that number of edges decrease. So, but instead I will say, okay, number of vertices must decrease. So I will put it here. Okay, so I know for sure that number of vertices decrease in this argument. So if I put it into the parameter, so then I'm fine. So far, I'm fine so far. But later I may have to modify. Okay, so therefore we may assume A intersection B is empty. What about the other case? Oh, well, if the edge set is empty, if you don't have any edges, then what does that mean? That means the right hand side, I mean, you don't have, so any set is actually a separating, any subset S is a separating A from B. So that means K is what? K is at most 0. Right? You cannot have a, if K is bigger than 0, then empty set is separating, but that's not possible. So if K is at most 0, then it's trivial, right? Then you must have a vertex decision, K vertex decision path, so then it's trivial. So we may assume that the set of edges is non-empty. Okay, why not? So let's pick one edge. Oh, but by the way, if you have an if E is a loop, then we apply the induction hypothesis. To G delete E. Why? Because loops doesn't do anything for the maximum number of vertex decision paths, and loops doesn't do anything for the set separating A from B, right? So if I have a loop, I can delete it and apply induction. But why can I apply induction? Well, now I modify this parameter just by adding number of vertices, I mean with the number of edges. So this will be my parameter for induction. What does that mean? That means I'm going to consider the minimum count example with this number as small as possible. Okay? So that's the same thing. Okay, so if I delete an edge E, then I don't decrease the number of vertices, but I definitely decrease the number of edges. And then by induction, I know that the theorem is true for G delete E, and that applies to our main situation. So the E is not a loop. Okay, so we are done by applying the induction hypothesis. So we can assume that E is not a loop. Now, what are we going to do? Well, let's contract E and see what happens. Okay. So if G prime has K vertex decision paths, from A to B, then so does G, right? because if you have a k disjoint path in G prime, now the contracted vertex, if it's outside of this path, then you're still fine, everything else is still path. If the contracted vertex is here, then what's going to happen is maybe the contracted edge was here, or the edge is here, right? But in both cases, you still have a path, right? So as long as G prime has path, as long as G prime has k vertices path from A to B, then G will also have such a path. Here, A, B, so when I contract, it may be possible that E has both ends inside A. In that case, new A is actually one smaller, but you can think, right? So this, if this was A and this is E, then in G prime, they could become one vertex, but let's say this is still fine. Let's just say that this is still A for convenience. All right. So that means, therefore, we may assume G prime has no k vertex disjoint path from A to B. So what does that mean? By induction hypothesis, the reason why I can apply induction hypothesis is because G prime has less number of vertices, G prime has less number of edges. So G prime has a set S. Oh, I should modify the claim. Okay. How do I? All right, let's modify the claim. So I said it's if and only. I said only one direction, but let's say both direction. And this is again true. And that's actually equivalent to the Menger's theorem, right? So if I don't have a k vertex disjoint path, I want to have a set of size less than k. Okay, so set of size less than k such that such that S separates A from B. So here you have a set S, A, B. This is in G prime. And S has size k, less than k. So that's why you don't have a k vertex disjoint path from A to B. But in G, you don't have such a set. So where is this vertex obtained from by contracting E? If that vertex is outside of S, then this S is still a separator separating A from B, because if I have a path not using this thing, because this is not a separator, this doesn't separate A from B, you must have a path. And that path is still a path, even if I contract any edge, right? I could contract E here, or I could contract E there. In any case, I still have a path, and that's not possible. What that means is, in G, this corresponding set should have a bigger size. Okay, so what does that mean? That means actually, so let's say this is S prime, both ends of E are in S prime. So since G has no set S, no set of size less than K separating A from B, the vertex of G prime obtained by contracting E, obtained from E, should be in in S. Oops, yeah. So that means, so if I uncontract, so here you have S of size less than K. If I uncontract, you have both ends here, so that means this S prime has size 1 more than S, and this separates A from B, and there's no set of no separator of size less than K separating A from B, so therefore this has to be exactly K, and size of S should be, right? So there is a set S prime of G of size exactly K having both ends of E such that G delete S has no path from A to B. So you have exactly K vertices here, which is S prime, and here's A, here's B, and the edge E is here. Now what we do is the following. Here's the strategy. I'm gonna apply induction to find the K paths here and K paths there, and just glue them together. Okay, how do we find the K paths here? Well, I will delete E. Then the theorem is certainly true, right? So because of induction, so what we do is, so we claim that G has K vertex disjoint paths from A to S prime. Okay, why? Well, we will apply induction over G delete E, right? If G delete E has a set X of size less than K separating A from S prime, so if A X S prime B, so you have a set X of size less than K separating A from S prime. Now then I claim that X separates A from B, but let's suppose not, right? So X is a small size set, and so by assumption, since there's no set of size less than K separating A from B, so G has a path from A to B, path P, not using any vertex of X, which means P must use a vertex of S prime, right? And right, if I have any paths from A to B, because S separates A from B, it has to use at least one vertex. So therefore, there is a path from A to S prime. G delete E has a path from A to S prime, not using E. So that's it. Contradiction. Because we said that it's a separating A from S prime, and but it has a path, so it's contradiction. Thus, G delete E has K vertex disjoint path by induction hypothesis from A to S prime. Oh, I don't have to say G delete E because if I have a, okay, but anyway, it doesn't matter. Yeah, I don't have to say G, so G delete E. All right. So now what we look is the following. So S prime B. So by this previous claim, I have a K disjoint path from A to S prime in G delete E, and I also have a K disjoint path from B to S prime by symmetry. And then we glue them together. GSK vertex disjoint path from B to S prime. So G delete E by the same argument. Now I claim that now when you combine these paths, you have a vertex disjoint path. What can go wrong, right? So how can you have so none of these paths on the left hand side will share a vertex because they were vertex disjoint. No two paths here shares vertex because of assumption. How about paths on the left and paths on the right? Can they share a vertex? So if I have a path here and I have another path here sharing a vertex, what can go wrong? Well, then I have a path from A to B not meeting any of S prime. That's contradiction because S prime separates A from B. So therefore, we get a K vertex disjoint path from A to B in G. So that's the end of the proof. Okay. So we use induction. All right. So now as a corollary, we want to prove a generalization of the Whitney's theorem for higher connectivity. So this is a corollary. So let A, B be two distinct non-adjacent vertices of G. So here I have A, B. Then when do we have a K internally disjoint path? So G has K internally disjoint path from A to B if and only if there is no set S which is subset of set of vertices minus AB such that G delete S has no path. From A to B. So it's a separating set. But in this case, the difference is that we don't allow deleting vertex A or B. So these two we don't delete. So why do we have a non-adjacency? Because if you have an edge from A to B, then no matter how you delete a vertex in the middle, you're gonna have at least one path. So the theorem, this corollary cannot be true. But other than that case, we have this thing. And the proof is not difficult because you have A and B. Now you take neighbors of A and neighbors of B. So G has K internally disjoint paths from A to B if and only if G has K no, not G, but G delete A delete B has K vertex disjoint path from neighbors of A to neighbors of B. That's same as saying by the Menger's theorem, G delete A delete B has no set S of size less than K separating NA from NB, and that means G delete A delete G has no set S of subset of VG minus AB such that G has, oops, did I say size? Okay, and size of S is less than K. No pass, okay, no pass from A to B, and size of S is less than K. Okay, so it's an easy corollary. Now another corollary of this, maybe it's suitable for homework, but maybe not. Okay, so let G be a graph and number of vertices is bigger than K, then it's 1. Then G is K connected, so now it's characterization of K connected graphs if and only if for any two vertices X and Y, for any two distinct vertices, let's say, G has at least K internally disjoint paths. From X to Y. So remember, we had a characterization of two connected graphs, and one of the characterization is like for graph with it's a graph with more than two vertices, and for any pair of vertices, you have a cycle containing them. Another way of saying same thing is for any pair of vertices, distinct vertices, you have a two internally disjoint paths. Now we want to have a generalization. So instead, I should say K. Instead of two connectedness, I have a K connectedness. And in order to say graph is K connected, we need to say that for any pair of vertices, you have a K internally disjoint paths from one to the other. Okay, so how do we prove that? And one direction is clear. If you have many paths, then no matter how you delete less than K vertices, for any two vertex, since there are K disjoint paths, one of them will not meet this small set. So that means deletion of any set of size less than K makes the connected graph. So this is clear. How about the forward directions? Now suppose G has no K internally disjoint paths from X to Y, and X and Y are distinct. Now all right, now we want to use this corollary. If X and Y are non-adjacent, then it's easy, right? Because of the previous corollary, if they are non-adjacent, then G has a set S of psi S, which is a subset of vertex set minus XY, of size less than k such that G delete S has no path from X to Y. Contradiction to the assumption, right? Contradiction to the assumption that G is K connected. All right. So we may assume X, Y are adjacent, right? So you have X and Y, and maybe you have not only adjacent, but you may have some number of parallel edges. But those are actually quite good because if you do have a parallel edges, you can what can you say? Well, if you do have a parallel edges, then you, I mean any edge, you delete one. You can use that as one of the paths, one of the internally determined paths. So what can you do? Now what you can do is we delete those edges from X to Y, right? And then so let's say we have M edges from X to Y. Now G prime, let G prime be G minus all edges parallel incident with both X and Y. So this is a smaller graph. Now it'd be nice if G prime is K minus M connected. So that's what we want to say. I deleted, actually we may say the following: G prime is K minus 1 connected. Why? If not, then there is a set X of size less than K minus 1 such that G prime minus X is disconnected, right? So here's a set X of size less than K minus 1 and graph is disconnected, so there's no edge from left to right. But in G, this is not G delete X is connected. Right? Well, the thing is, so that means the only place that are different is the edge between X and Y. So you have a X on the left hand side, Y on the right hand side, and these are parallel edges. But anyway, it's not very important. All right, and now what we do is, so that, okay, now how many vertices do we have? So here you have less than K minus 1 and you have 2 more vertices, and the number of vertices of graph G is bigger than K, right? But here you have at most K minus 2 vertices and 2 vertices. So therefore, there is at least one vertex. Not in X union A, B. Right? And it could be here or there. Why am I worried about that? I mean, the thing is, so the G delete, so in the, so G delete X union, oh, did I say AB or XY? XY in this theorem. Yeah, so XY. So either this or G delete X union Y is disconnected. Why? Because, for instance, if there's an element here, then I take this thing, and if I delete all of these red boxes, then there is no edge from left to right, and that's disconnected because you have at least one vertex here. But maybe this is empty except this guy, but then you take this as your set to delete, and graph is disconnected. Okay, now that means what? Contradiction, because X union X is too small. X union Y is small. Yeah, it's contradiction to the fact, to the assumption that G is K connected. So G prime is K minus 1 connected. So by the previous corollary, oops, by previous corollary, G prime has, and now since X and Y are non-adjacent because I have deleted all the edges, has K minus 1 internally disjoint paths. From X to Y, and add one path by using the edge XY, right? So then you have a K internal disjoint path. So we are done. Okay, so that's the proof. All right, so that proves the graph is K connected even on if you have a K but internally disjoint path from X to Y, and I don't care whether these two vertices are adjacent or not. There are other versions of Menger's theorem, and people call it still Menger's theorem. Like, let me just mention. So instead of the vertex disjoint path, you may talk about the edge disjoint path. And then instead of a vertex cut, you have to delete the edges. Right? So how many edges do you have? How many edge disjoint paths can you have? Well, that's equal to the maximum number of edges that you can destroy so that there's no path from A to B. And how do we prove that? In order to prove it, you apply Menger to the line graph. LG, remember? The edges become vertices. So the edge disjoint path in the original graph is almost the same as the vertex disjoint path in the line graph. And then once you make a line graph, you can apply the vertex disjoint path version, our version of the Menger's theorem, and that will give you the proof. All right, now let's move on to the three connected graphs. So here's the key theorem that allows us to apply inductions, and this will be used later for the proof of Grotowski's theorem. So here's the theorem. So let G be a three connected graph, then G has an edge E such that G contract E is also 3 connected, unless graph is too small. I mean, it's equal to 4. Right? If graph has 4 vertices, when you contract an edge, you may end up with a 3 vertex graph, and that's never 3 connected, because 3 connected graph must have at least 4 vertices. And this will be a key theorem later when you try to prove the Grotowski's theorem. So let's prove it. All right, so first we can assume G is simple, because if this theorem is true for simple graph, then it's true for graphs with parallel edges or loops, right? So because the connectivity doesn't change by adding loops or parallel edges. So suppose G contract E is not reconnected for every edge E. But you can still say that G contract E is 2 connected. Why? Because if you have a cup vertex, I mean, it's connected anyway. You contract an edge from connected graphs, so then you have connected graph. If you contract an edge in a 3 connected graph, if it has a cup vertex, then when you uncontract, then either you have, I mean, you may have a picture like this, where this is E, and it's still, I mean, you have a vertex cut of size 2. It's contradiction, right? G doesn't have such a thing. So G contract E is 2 connected. So what does that mean? But G contract E is not reconnected. So this is my drawing for G. So in G contract E, you have there is a vertex cut of size 2. But in G, there's no vertex cut of size 2. So what does that mean? So in G contract E, now I must have a vertex cut of size 2, something like this. In G, if the vertex formed by contracting E is outside of this box, then this will stay as a vertex cut. And that's not possible because G is 3 connected. So therefore, these vertex, the edge E, have both ends inside this set. Right, so so you must have a vertex cut of size 3. So G contract E, no, G has a vertex cut of size 3 containing both ends of E. All right, so let's say this is W. Now, for any edge E, I have a W. Okay, so maybe WE. Okay. So choose E. So I'm gonna choose E and WE so that the largest component of G delete WE is as large as possible. Remember, there are only finitely many choices. Right? You only have a finitely many choices of choosing E and vertex cutoff size 3. So among them, you choose the pair so that the largest component is as big as possible. So let's say this largest component is HE. So this is HE. So here's WE, and there are other people, and you have both edges here. So let's say the ends of the E is XY, and let G be the vertex in WE so that WE is XYG. Okay? Now this is X, this is Y, this is G. Now, graph is 3 connected, so each of X, Y, G must have neighbors in every component. Okay, since G is 3 connected, each of X, Y, G has a neighbor in every component of G delete WE, because, for instance, if one doesn't have neighbors to HE, one component, then the other two will be a separator of size 2. That's not possible. All right. Now, what we now do is to find another edge that we get a larger component. So how do we do that? So I'm going to choose, so by this property, there will be some edge here having neighbor U, let's say. So let's say this is a F. So what do you do? So choose a neighbor U not in HE union WE. Neighbor U of G. So let F be GU, this edge. And then there will be, so now we consider WF and HF. All right. So what's going to happen? So here we had a WE. So you have X and Y and F. Now WF must contain these two vertices and one more. Right. And this, so let this one more vertex, let's call it V. So that WF is equal to, so this is G, this is U. So G, U, and V. All right. So where is this V? I don't know, right? But what I can say is the following. If V is not on the left-hand side, here's HE. If V is not on the left-hand side, then HE is connected, and we are deleting these 3 vertices. I mean, V could be one of XY, right? So this could be the WF. So after deleting WF, HE together with X or Y will stay in the same component. With X or Y other than V will be in the same component of G delete WE. No, WF. Wait, that's weird, because we chose E and HE so that the largest component is as large as possible. but we kept every vertex in HE together with one more vertex. So that's a contradiction to the choice of E and HE. So V is not in V is in HE, but now so V is here is adjacent, but both X and Y have neighbors in HE, right? Now what we end up is, we know that right? Yes. So HE delete V is connected. Why? Okay, let's not say that. There's an easier way. Let's pick a vertex. Let's pick vertex outside. Let's say outside, okay. Now, graph is 3 connected, so for any vertex inside HE, I must have a 3 internally disjoint paths. So those 3 paths must use X, Y, G exactly once. And so among 3 paths, one of them uses G, one of them potentially uses V, but still one remains, right? So that means I must have a path from HE to vertex outside by using these 3. So that means since G is 3 connected, for every vertex, can I use W? Yeah, yes, W in HE minus V, there is a path from W to X or Y not meeting V or G. And that's enough. That means HE minus V union XY induces a connected graph. So they are in the same component. But the number of vertices in this component is larger than size of HE because we delete 1, but we added 2. So that's again contradiction. Okay, so this is a kind of proof that uses the maximality. So we want to find particular edges that we can contract, keeping 3 connectedness, and the idea is to come up with a particular choice of E and the component, and there's no better yeah, I mean that. So this proof shows that if you keep, I mean, this another way of viewing this proof is that if you repeat this argument, right, you choose one edge and find the largest component, and then you try to pick another edge and find the largest component. You try to pick another edge and find the largest component. If you repeat this process, at some point you're gonna end up with a situation where when you contract, graph is 3 connected, so you cannot find the separator of size less than 3. Okay, so that's it. So in the next lecture, we will prove a similar theorem for simple 3 connected graphs. Okay, that's it.